So can you see my screen? Is it visible to everyone? Okay, great. So in the last class, we have seen till this point. I've given this example also, and let's recap this. So suppose you have given this image. Suppose this is the image given to you, and if I say you like apply the convolution layer over this, okay, and I'm also giving you the filter size, okay. So the size of this image is 7 by 7, and you just apply 3 by 3 filter over this. So what you will do, you will take, firstly you will take filter and will put here. Okay. So what you are doing, you are putting the filter on this center pixel. Okay. So the center value of the filter will be given here, and the left side this side, top this side, bottom this side, and right hand this side. So in that way, like you are just fitting 3 by 3 filter at this location. And then you are doing the dot product of every value. Just dot is like point wise multiplication. And then finally summing these all the things. And that will give you one value as an output. Okay. Okay. So whenever I'm saying like I'm going to apply filter, that means it's like we are doing the dot product of the value of the filter and the value of the particular portion of the image. Okay. So in this way, you are getting, by doing this, you are getting one value as an output. Now it's done for this. Then you will go just leave one space. Now you are here. Your center pixel of the filter is now your center value of the filter is here, and then again you apply this filter at this point at this portion, and you will get one value for this. So for first convolution you got one value. Now again you have done this convolution, you got one value, and now you are here. Now for this you will get third value. Now you are here, you got four values, and so you got five values in this direction. And similarly, now after doing this, now you shift one, you'll just leave one row from the top. So now again we start from this place, and again you'll move in the similar manner. Okay. So in that way, in this direction also, you can have five different values, or five distinct pixels, or five distinct position where you can put the filter. Okay. So in this way, you can get five this direction, five by five matrix. So when we have 7 by 7 image, and if you're applying 3 by 3 filter, you'll be getting 5 by 5 image. So your size is getting reduced. Why? Because of the center pixels. So if I like for every center pixel, you're getting one output value. So you can put center pixel only at this point. You cannot put here. You cannot put the center value of the filter at this point, because if you put the center value of the filter here, then left hand side you do not have anything. So you cannot put here. So you cannot start from this point. So you can only start from this point. Similarly, you cannot start from this point because this side there is nothing. So if you put the center value of the filter at this point, then you will be not having anything on the top side. So you have to find the position or pixel where you can fit the filter. So you have to find the pixel which can be working as a center pixel for applying this filter. Okay. So you can have only five different pixel here that can be considered as a center pixel for applying this filter. And same thing happened in this direction also. So in that way, you will be having only 5 by 5 distinct position, distinct uh, pixels where you can fit this filter. Or in other words, I can say like where the center value of this pixel can be put. Okay. Because you have to like for the center value, you should be having like you will be considering one pixel as a center pixel. And then you will be having all the surrounding pixels, and then you will be applying the filter on that. Okay. So just like when I want to ask something, some information about this pixel. So what I'm doing, I'm not just asking information from this. Instead, what I'm doing, I'm trying to ask the information from this as well as the neighbor of this. So I'm considering this 3 by 3 region. That means I'll be having 8 neighbors because 3 by 3 total 9 pixels you are considering. And one is the center pixel. This is the focus pixel where we are going to give the focus. Or I can say like we are going to get the information about this pixel. But just asking the information from this pixel will not give you very good information. So what you are doing, you're applying, you're asking the things from this pixel as well as the neighboring pixel of this. And then you are aggregating all those information, and that will be the representation, or you can say the defined value of this pixel. And this is the thing that you are doing for every other pixels. Okay. But you cannot do for this. You cannot do for this. You cannot do for this because for this there is nothing in this side. So you cannot consider that pixel as a center pixel. Okay. So you can only consider 5 different pixels in this direction as a center pixels and 5 in this direction. So we have 5 by 5 matrix that you will be getting. So in this way, your size of the image is getting reduced. So if I see like what is the output size that I'm getting, then you can like just I also have shown through the example and through the visual stuff, but you can also apply the formula. So if I just ask you like what would be the size of the output, you can directly apply this formula, W minus K plus 1. So W is your like initial width. So in this case, your initial width is 7. K is the filter, the width of the filter. So width of the filter is 3 and plus 1. This will give you the new width. Okay. So 7 minus 3 plus 4 plus 1. So 4 plus 1, 5. Similarly for height also, h minus k plus 1. Because you are taking a square filter, so your height and width of the filter is same. So 7 minus 3 plus 1 equal to 5. Okay. So this is the size. So using formula also you can get this information. But by just looking this visual stuff, you'll be able to you'll get to know like what will be the height and what will be the width after applying this convolution filter. Okay. Now what is the problem here? Now we have applied the convolution filter, and now whether we are happy with this or we feel that there is some problem. Actually, there is some problem in this case. So when I'm applying the filter, what I told you that every time you are considering the center pixel and you are going to refine the value of the center pixel. So you want to get the information of the center pixel, but just for getting that information, you are taking the help from the neighbors so that you will be not your information will be not fully biased towards this guy because this guy might give you wrong result also, wrong information also. So why not we consider the neighboring pixels? And that's why you're applying the filter, because filter is also it's also giving focus on the neighboring pixel. So but goal is to consider this only. So whenever you are applying filter over this, you are looking this pixel only. But for getting the information of this pixel, you are also taking the help from other neighboring pixels who are like neighbors of this pixel. And in this way, you are doing for every pixel. Now the problem is that if I do it, I'm leaving some of the pixels. I'm not considering every pixel as a center pixels. Why? Because your filter is not getting fit. So I cannot fit filter here. I cannot consider this as a center pixel. I cannot consider this as a center pixel. I cannot consider this as a center pixel because there is no space. There's nothing is there in this side, nothing is there in this side, nothing is there in this side. That means I cannot get the refined information of this pixel. I cannot get the refined information of this pixel. I cannot get the refined information of this pixel. So, so what the problem that we are getting here, that is like we are just leaving the all the corner pixels. So while getting the output, you are not giving focus on the corner pixel. So you are losing that information. So when you are working on the image, this is the full image, and you consider these all the pixels. But since due to your filter problem, you will be not able to consider these all the corner pixels. And in some of the cases, the corner pixels could be very important. Maybe a lot of good informations are there on the corner pixels. And if you do not keep focus on the corner pixel, it might give you, I should not say wrong result, but it may not give you very accurate result or very accurate features that you wanted to get because you are not considering some of the pixels from this image, and those pixels could be important pixels. Okay, so why not we consider those corner pixels also? So what we do for considering the corner pixels, we do the zero padding. So suppose this is the image that is given to you 7 by 7. Now what I'll do, I'll do the zero padding. I'll add the zero both in every side. So I'll add zero here. I'll add one row up like from the top, and I'll also add one row from the bottom. Similarly, I'll add one column this left hand side and one column right hand side. Now if I do it, now what will happen? Your original image is only this much, the inner side, the inner area, only this much. These are like just we are adding some extra pixel which are having zero value. Now if I apply filter, if you are going to apply filter 3 by 3 filter, now you will be able to consider the corner pixel also. Now you can put the filter at this point also, because at this side we have the column, this side also we have the row. So if I put center of the filter here, I can easily fit it. Sorry, it should not go in this way. Yeah, I can easily fit it. So in that way I can fit this filter at every pixel of this image. And you know that for every center pixel, you'll be getting one value in the output. So since I'm able to fit at every position of this, that means I'll be getting the image size of 7 by 7 only. So in this way, now you're considering every pixel of the image. Now you're not losing the information of the corner pixels, which were happening in the previous case. So in the previous case, we were not able to consider the corner pixels. Now by doing zero padding, you are able to consider the corner pixels. Okay. So in general, when we are going to apply the convolution filter, you will do the zero padding so that it will cover every pixel of the image. Okay. So it depends. Zero padding is depends. So since you have applied 3 by 3 filter, that's why you have taken this one column this side, one column this side, one row this side, one. But if you go for some maybe 5 by 5 filter, then scenario will be different. Then maybe you need to consider two rows this side, two rows this side, two column this side, two column this side. Okay, so it depends on the size of the filter. Okay, so our goal is to get the same size output, whatever we had in the original input. So in the original input, we had size 7 by 7. And since in the previous case, when we were applying 3 by 3 filter, we were getting 5 by 5 size image as output, or 5 by 5 feature map as output. But now I want same size output because I want to consider every pixel of the image. Okay, so based on the filter size, you do the zero padding in such a manner so that it will give you same size output, whatever we had, the original input size. So in this case, the original image is of 7 by 7. And you have added some extra bit, extra values for considering every pixel of this image. Your image is only the inside this part. Outer part is not your image. It's just like you are adding some zeros so that it will give you it will consider the every pixel of this particular image. Now when you do zero padding, your formula, the output size formula would be changed. So now previously, like your formula was this. Now you add this 2p. So 2w minus k plus 1 plus 2p. 2p, p means your padding. Okay. Remaining things are same only. So now if I'm saying I'm doing padding 1, if I'm doing padding 1 in the width direction, that means I'm adding one column here and one column here. So I'm adding one column both sides. So whenever I'm saying padding equal to 1 for the width, that means I'm going to add one column this side and one column this side. Okay. So in that manner, you'll be having, suppose this is the original size of the W was what? In this, initially it was 7 by 7, but like, yes. So it was what? It was 7 by 7. So width was 7. W minus k is 3 plus 1 and plus 2 into padding is 1 in the width direction. So padding is 1. So if you do it, 7 minus 3, 4 plus 1, 5 plus 2, 7. In the similar manner, you can also find the new height. That will be 7. Okay. So in this way, now you are not losing any information. See, because you are considering every pixel of the image, every pixel of the original image. Now let's see one more concept, that is receptive field. So when you have given this 3 by 3 image, if I'm giving you this 3 by 3 image, not 3 by 3 image, if I'm giving you this bigger image, and I'm saying you like I'm going to apply 3 by 3 filter here. Okay. If you apply 3 by 3 filter over this image, you'll get the output. Again, I'm saying you like I'll apply 3 by 3 filter over this. So whatever output you got from the first convolution, now that will be considered as an input for the second filter or second layer or second convolution layer. Okay. Now if I apply here 3 by 3, now these two are like different things. If I say like what this 3 by 3 is doing, this 3 by 3 is just looking this 3 by 3 region of the image. If I'm saying like what this 3 by 3 is doing, so this 3 by 3 is also looking the 3 by 3 region of this feature map. But this feature map is not the original image. From where it is coming? It is coming from this image. And if I see this 3 by 3 region, this is projected to one bigger region from the original image. Why? Because for every 3 by 3 region from the original image, this is the original image, this is the original image, and what you have done, you applied filter to every 3 by 3 region, and you got one value for that. For every region, you got one value, every value, one value, one value. Okay. And now here also you are applying 3 by 3 filter. Here you are looking this 3 by 3 region. But this 3 by 3 region is not the same in the original space. Why? Because in this 3 by 3 region, every value is coming from 3 by 3 region of the original image. So I'm trying to see only this 3 by 3 area, but in actuality, your receptive field is larger. So you are not only seeing this 3 by 3 region of the image. Instead, if you go back, this 3 by 3 region is the bigger area in the original image. Okay. Again, if you come here, again, if you apply 3 by 3, you'll get new image. Again, you apply 3 by 3 here. Now, every time you are applying 3 by 3 filter only. So you can say like, hey, I'm applying 3 by 3 filter, then it's just looking the 3 by 3 region of the image. But your image is different. Your image is transformed image of the original. So here, this was the original image. Here you applied 3 by 3 filter. You are just looking the original image, 3 by 3 region. Now from this image, you made the new image. Now in this new image, every pixel is the representation of 3 by 3 area of the original image. And what you are doing, again, you are taking this 3 by 3 value from here. So in this 3 by 3 value, every value is like coming from 3 by 3 region of the original image. So receptive field of this is larger. So you are seeing this 3 by 3 region only, but this 3 by 3 region is not same as this 3 by 3 region. Because in this 3 by 3 region, every value is coming from the 3 by 3 region of the original image. So you are applying same size filter, but your receptive field is getting increased. So if you just see the original image, then you are looking the bigger area. So by the layers, you are looking the bigger area of the image indirectly. It's not happening directly. One way is like you can directly apply one bigger filter here, and you can just apply filter and you can get the new image. But that we are not doing. We are applying the bigger filter. Like your filter size is remains same, but your receptive field is getting increased because every time you are applying on the transformed image, and that transformed image is coming from the filter which you have applied on the previous input. Okay. So by doing this thing, maybe at after certain time, you might be reaching at this point where you got only one value. Now this is the final value that you got. So after applying multiple 3 by 3 filter, you might be reaching at this point. Now if I say you like, what is this? You can easily say, or maybe this is like, maybe it could be like 3 by 3 value. So if I ask you like what this 3 by 3 value is, you can say like this is the representation of full image. Because if I go back, if I go back, actually I have seen the full image. So I have not seen the full image in a single shot. Instead, I have applied multiple filters in the sequential order. And by applying multiple filters, my receptive field is getting increased. It means I'm applying same size filter, but this filter is looking the bigger area of the original image. So that means your receptive field is getting increased. You are applying same size filter, but indirectly you are looking the bigger area of the image because this is the transformed image which you are getting from the previous input. And every time you are applying on the transform. Now if I see like what is this one value here, this one value is coming from 3 by 3 region from here. And what is this 3 by 3 region? This 3 by 3 region, if I just see one pixel from here, this one pixel is coming from again 3 by 3 region from the original image. In that way, just applying the same size filter every time, your receptive field size is getting increased. So you are looking the same, see, you're applying the same size filter, but that same size filter is looking bigger area of the original image. Because at the end, your goal is to see this whole this image. And you started with seeing the smaller portion of the image, but by the layers, by the different convolution layers, you are looking the image from different scale or from different receptive field, or maybe you can say like larger receptive field. I'll give you one example, then it will be more clear. So suppose I have given you 7 by 7 image. Again, take the same image which we have seen before, 7 by 7 image. And if I say you apply 3 by 3 filter over this, so if you apply 3 by 3 filter over this, or just take not 7 by 7, just take 5 by 5 only. For the sake of easiness, take 5 by 5 only. And if I tell you to apply 3 by 3 filter over this, now what will be the output? Your output will be what? Your width will be, you are not doing any zero padding. Let us ignore the zero padding. Then your width will be, new width will be what? 5 minus 3 plus 1. That will be 3. Height will be also 5 minus 3 plus 1. I'm just applying W minus K plus 1 formula, okay? And H minus K plus 1 formula, okay? So it will give you 3 by 3, okay? So just applying 3 by 3 filter over 5 by 5 image, you got 3 by 3 image, okay? Again, if I apply one 3 by 3 filter over this, I'll apply here, this will give you one single value, okay? So what is happening? I'm applying two 3 by 3 filter and I'm getting one value. This is similar to applying one 5 by 5 filter over this image. Even I can directly apply one 5 by 5 filter over this image. So if I apply the same size filter over this image, what will happen? It will give you one value because it just in a single shot, it will cover full image. It will give you one value. So you're applying two 3 by 3 filters is equivalent to applying one 5 by 5 filter. So I told the same here in this case. So maybe applying 3 by 3, 3 by 3. If you're applying two 3 by 3 here, now at this point, this is not only 3 by 3. It's like you already have applied 3 by 3 before, and then you have applied this 3 by 3. So now this is equivalent to 5 by 5 filter. So by the layers, your size of the filter is getting, or I should not say size, but receptive field size is getting increased. So your size remains same, but in actuality, you are applying the bigger filter, which is not visible, but that is happening indirectly. Okay, so the problem is if you have very larger image and if you apply very small filter, then it may take a lot of steps, a lot of layers to reach to the maybe one value or maybe some few values at the end, or maybe the global values at the end. So what you want to do? When I was explaining when like in the when I started this CNN, what I told you that CNN is just like we are looking the Earth from the like we are looking the Earth from the different distance. So this is the closest distance from where you are looking this. Suppose this is the Earth. So these are the lens. You're looking the Earth from these lenses, and these are like very close. That's why you are able to see the small portion of the image or small portion of the Earth. And by the time you are moving ahead. Why? Because at the end we have to capture the information of the full Earth or full image. So at the end, I want to capture the information of the full image also. So start from the small lens or from the close distance and then move far. So whenever I'm saying move far, that means I'm looking the bigger portion of the image or bigger portion of the Earth. And finally, at the end, I want to cover full image. So I want to cover full image so that like then only I'll be able to get the information about this, the whole Earth or whole image. So if I go in this way, and if your image size is very large, then it will take a lot of time to cover full image. Okay. So this is like one type of problem that you may occur while doing this experiment. So solution would be like, why not downsample the image inside the network? Because if I'm taking very large image, it's problematic. So every time, can I reduce the size of the image? So you can do it. It's very easy. And for that, who will help you? Your stride will help you. So when I was explaining this thing, I told you that in the previous cases, we have considered stride equal to 1. So every time you are just applying the filter and leaving one space. Now you will be here. Next time you will be, maybe you will be here. Next time you will be here. So every time you are leaving the one space. And that's why you are getting, your image size was getting reduced, but not drastically. It's like just little bit reduced in the size. So when we were applying 3 by 3 filter over the 7 by 7 image, we'll be getting 5 by 5. Now, if we change this stride, so in that case, stride was 1. You're leaving just one space. Now, suppose I leave two spaces at a time. What will happen? If I leave two spaces at a time, then again your size will be also affected a lot. So what you'll do? You will start from here. For this, you'll get one value. Now you have to leave two space. So next time where you will be? Now you'll just come here and take this. You'll get one value. Next time where you will be? I'll be at this point. So if I take a stride equal to 2, you can only have three center position or three center pixels in this direction. Similarly, in this direction also we have 3. So you'll be getting 3 by 3 image. So there is the important role of this stride. So stride can also reduce the size of the image drastically. So if you want to reduce the size of the image drastically, just take larger stride. Okay, and that will reduce the size dramatically or drastically. Okay, you can see like firstly we were here, now you are here, and now you are here. So you have only 3 position where you have fitted the filter in the width direction. Now let us make the final formula. So we have added the zero padding. Now we have also, there is a role of the stride. So in the previous case, stride was 1. But if you change the stride from 1 to 2 or from 1 to 3 or from 1 to 4, then what will be the effect on the output size? And you already have seen that when we were changing stride from 1 to 2, your image has been reduced by almost half of the original image. Okay. So let us see like how to formulate this thing, how to write the formula for this. So now we have whole picture. We have seen all the things, filter, padding, and then stride. Now we can make the formula. So this would be the formula. So this W is like original width minus the width of the filter plus 2p, zero padding, and then divide by stride and plus 1. So now let us apply this formula for the previous cases and just see like whether we are getting the same size or not. So in the previous case, when we had 7 by 7 and filter was 3 by 3 and the stride was 1. And suppose we are taking zero padding equal to, we are not doing any zero padding. That means padding equal to 0. Now what will be the output? So we'll be having W, suppose W is 7. So 7 minus K, the height, width of the filter is 3, plus 2 into 0, divide by stride. Suppose your stride is 1, plus 1. So this will give you what? 7 minus 3, and you will be having plus 1 here. So 7 minus 3, that is 4. 4 plus 1, 5. Similarly, for the height also you will get 5. And the same thing we were getting in the previous case. So this formula is valid for every cases. Now let us take the stride 2. So if I take a stride 2, then I'll be having 7 minus 3 plus, I'm not doing any zero padding, so 2 into 0, divide by, now stride is 2, so 2 and plus 1. So 7 minus 3, 4. So 4 by 2 plus 1. That is 2 plus 1, 3. So this is your width. And similarly, you can do for the height. So you'll be also getting height equal to 3. So when you are doing a stride equal to 2, you are getting output size 3 by 3. So now this is the standard formula that you can apply. You no need to memorize all these things. Just keep this formula in your mind and you can easily get the size, like what would be the output size, what would be the height of the output, what would be the width of the output, and what would be the number of channel. Now let us see one example. So suppose I'm giving you this image. This is like 30 by 32, 32 by 32 image, height and width 32 by 32, 32 and 32, and channel is 3. RGB image. And what I'm saying you, apply 5 by 5 filter over this image. And you have to apply 10 such type of filters with stride 1 and padding 2. Now if I ask you like what would be the output size? What would be the width, height, and the channel of the output? So let's define the output. Let's see like what would be the output size. So you know that number of filters gives you the channel of the output. So since you have applied 10 filters, so for one filter you'll get one image. So you apply 10 filters, you'll get 10 image. And that means you will get 10 channel. So you can easily say channel would be 10. Now how to define the height and width? So for the height you have the formula. So what is that formula? So for height, if I say height equal to, this is the new height, h dash equal to h minus what? Filter, the height of the filter. So maybe I write kh, filter size, plus 2 of padding divided by s plus 1. Now what is your height? Your height is 32. What is the filter, the height of the filter? That is 5 plus 2. And what is the padding? Padding is 2. So 2 into 2. So as I said that when I'm saying padding equal to 2, that means you are adding 2 this side to that side. And that's why this is 2 of P. Okay. So 2 into 2, 2 divided by stride. Your stride is 1 plus 1. Now what would be the answer? So 32 minus 5, that is 27. And 27 plus 4, 31. 31 divided by 1, that is 31. 31 plus 1, it will give you 32. Now similarly for width also you can apply the same formula. So W dash equal to H minus K of W plus 2P divided by S. It should be W. So for this also you'll be having W dash equal to W minus K of W plus 2P divided by S. So W is what? Your 32 minus filter is a square filter. So KH is also 5 plus 2 into 2 divided by 1. This is tried plus 1 plus 1. You'll get the same size. So what is the output that you are getting? The output size is 10, 32 by 32. So in this way, you can calculate it. It's very, very easy. Okay, you have to just keep the formula in your mind, and that will give you the answer. So you can see here, we are getting 10 into 32 by 32. So your image size is not getting reduced. Why? Because you have added padding. But your channel is getting increased. Why? Because you have applied 10 5 by 5 filters. Okay. So in this way, you can find the output size. Now, if I ask you what is the like how many parameters we are learning here, number of learnable parameters, then how will you calculate it? You know where the parameters are involved. Your parameters are involved in the filter. Okay, because you are going to learn the filter. So whatever filter we are taking here, these are not fixed filter. All the values, whatever values we have in the filter, those values would be learned. So filter itself has to learn like what I have to see from the image. Okay. So your filter is contributing in the parameter. So whatever filter you have, that will give you the parameter, and you are going to learn it. So that's why this is like learnable parameters. Okay. So let us see like how many parameters we need to learn. So if I just see one filter, so what is the dimension of the filter? We have 5 by 5, but is this only 5 by 5? No. So whenever I'm saying 5 by 5 filter, that means I'll be also having channel, because your the channel of the filter should be matched with the channel of the input. So channel of the input is 3. So 3 will come automatically. So this is not only 5 by 5 filter, it is like 3 into 5 by 5 filter. So this much weight you need to learn for one filter. And you also know that you will be having one bias. So one bias is involved with one filter. So these many weights you need to learn for one filter plus one. Should write in this way. So 3 into 5 into 5 plus 1, and you are going to learn 10 such type of filter. So if I just compute this thing, 10 into 76, that will give you 760 parameters. So you are going to learn 760 parameters in this layer, in this convolution layer. Okay. Now let's see. Yeah, so here the same thing we have calculated. So these are the weights, one bias, total 76 value for the one filter, and you have 10 such type of filters, so 10 into 76. Now the next question is number of multiply addition operation. How many multiplication we are going to do here? Let us ignore the addition part, because addition part is not costly. But you know that whenever you are doing multiplication, multiplication is the costly process. So need to see like how many multiplication we are doing in this case. So when you are applying the convolution filter, how many multiplications are happening in this case? Now this is the tricky question. Now let's see how to define, how to find the total number of multiplication operation. For this, let us see the output. So what is the output that you got? I got this size output. Okay. So you have 10 into 32 into 32. That is the size of the output. Now from where you are getting this output, or how you are getting this output? If I just take one value from this output, this is the matrix 32 by 32 matrix, and you have like 10 channel. Now just pick one value from this. How you are getting one value in the output? It's coming from applying the filter over the image. So you have the 5 by 5 filter. So you have like 3 into 5 by 5 filter. This was the filter size. And what you did, you took this filter and you applied over the image, one portion of the image. And in that region, what is happening? Dot product is happening. So the value of the filter will be multiplied with the corresponding value of the image. So this is like element wise multiplication, which is happening here. Okay. So how many multiplication you are doing? Just applying filter on this region. You are doing 3 into 5, total 75 multiplication. Because every value in the filter is getting dot product with the corresponding value of the image. So 75 element wise multiplication is happening. So total 75 multiplication is happening. And what you are getting? You are getting one value in the output. You know that every just applying filter on one region is giving you one output. And how many outputs you have? So for getting one output, you are doing 75 multiplication. So what is the total number of multiplication? So your total number of multiplication is 10 into 32 into 32. These are like total number of output elements. And for getting one value in this, you have to multiply 75 values. Why? Because this is your filter size. And your filter is getting multiplied with the image. So these number of multiplication you need to perform. Okay, so whenever you are going to design neural network, you also need to see the number of computation, number of multiplication, because multiplication is very costly process. So we need to see, because if you are doing a lot of multiplication, maybe it may take a lot of time to converge. So suppose you are going to train the model, and you have a lot of multiplication operation, maybe millions or maybe trillions of multiplication that you are performing. In that case, it might take a lot of time to train for one epoch. So we also have to keep these all the things in our mind while designing the architecture. So one part is like your parameters. So we have to somehow reduce the parameters, because you know that your parameter is somehow related to the memory, because you are going to store this parameter. You are going to store these all the values in your memory, because these are the weights, and those weights are going to multiply with the input. So you have to store this thing, but at the same time you also have to see like how many multiplication, because this is about the space complexity and this is about the time complexity. So you have to keep these two things in your mind whenever you are going to design the neural network or this deep learning architecture. Okay, again we'll deep dive into this, like when we'll be explaining the CNN architecture, then we'll go through these all the stuffs, learnable parameters, multiplication operation, and then we'll see like we'll try at that time we'll try to interpret like what is the effect, how different architectures are having this multiplication operation parameters, how they are changing across the different architectures, and what are the advantages, what are the disadvantages. So everything we'll see later, like when we'll start the CNN architecture. You can see here like the same thing that I told you. So total number of output, this, and for one output you are doing 75 element wise multiplication. So total is like this much. So 768K multiplication we are performing in this case, just for the one layer. Okay. Now let's see one different type of filter. So till now I just told you like we can we can take like 3 by 3 filter, 5 by 5 filter, maybe different size of filter. Can I take one by one also? And if I'm taking one by one, what is the significance of it? Why I'm taking one by one? What is the importance of taking one by one filter? Because the goal was that, like what I told, that if I'm applying 3 by 3 filter over image, let us take this area. So what I'm trying to do, I'm trying to get the information of the center pixel with the help of neighbors. That's why I'm also considering the neighbors here. Now, if I apply one by one filter, then it means just like I'm giving focus on this area, I'm not giving the focus on the neighbors. Then what is the significance of this one by one filter? There is uses of this filter, and this is generally used for reducing the channels. So suppose you have given this filter, you have given this input, which is having 56 by 56 height and width, and it is having 64 channels. Now, suppose I want to reduce the channels, because you know that in the channel you have all the information. In the channel also you have all the information, because one channel is coming from one filter. So you have like, suppose I consider this pixel. This pixel is having 64 different values in the channel, and every value is different because it's coming from the different filter. Since you have applied 64 filter in the input, that's why you got 64 channel. And these all the informations are different because every filter is doing different thing. But if I just see like what is this, what I can say about this all the stuffs, actually these all the values are the representation of the same pixel, but it is having different type of information of the same pixel. So why not we aggregate it? So sometimes we need to aggregate this information. Sometimes we also need to reduce the channel, because at the end you have to go to the global information, because at the end you have to, like, you will be reaching to the very few pixels, and then you will be using the fully connected layer to do the classification if you are doing the classification. So somehow we have to reduce the channel. Okay. So one way is like you apply one square filter, like 3 by 3 filter, 5 by 5 filter, and then you in that way also you can do it. But that is slightly costly process, because you can apply 3 by 3. So this is also taking this 3 by 3 region. But if I apply one by one, this is just considering one pixel. Okay. But it's looking the channel. So if I'm saying one by one, this is not only one by one, it is one by one by, I should write 64 into one by one, because channel will come automatically. And what is the channel size? Channel is 64. So if I'm saying one by one, that is not only one by one, it's like 64 into one by one. And you are multiplying here. And suppose I'm multiplying 32 such type of filters. So for one filter, I'll get one image. I apply 32 filters, I'll get 32 images, and that will be the channel. So 32 channel, and your height and width will remain same, because you are considering every pixel, because your filter size is only one by one. Okay, but you are looking in the channel. So you are aggregating the information of the channel. And this is required sometime, because, and generally when we apply this thing, we apply this one by one filter at the end. So when, suppose you are applying, you are looking the image, you have applied the 3 by 3 filter here, you have got the new image, again you apply 3 by 3 filter, you got the new image, again you apply 3 by 3 filter. By the layers, your image is getting reduced, or you can say the representation of the image is getting reduced. Okay. But what we generally do, when just by going in this side, the general practice is every time we increase the number of filters. Since I know that my height and width are getting reduced, so we have to store some of this type of information, because if you're losing this information, this means if your size is getting reduced, that means you're losing the spatial information. But if we lose most of the spatial information, then that will be the problem. Okay, so why not we store some of the spatial information in the channel? So the general practice is when we apply the filter by the layers, number of filters are getting increased. Why? Because your image is getting decreased. So if I apply 3 by 3 filter, maybe I apply here maybe 10 filters. Maybe in the next layer, I'll apply 20 filters. Maybe in the next layer, I'll apply maybe 30 filters. So by the layers, I'm just increasing the number of filters so that some information will be stored in the channel. Because when I'm applying 30 filters, that means I'll be having 30 images in the output. And in the other words, I can say like I'll be having 30 channels in the output. So we are somehow storing the information in the channel. So maybe at the end, you will be having a lot of information in the channel because the channel size, number of channel would be very large. So at that point, suppose now you are moving toward the classification. Suppose at the end you have to do the classification. So you have to apply the fully connected. But before going to that, we also have to aggregate the information. And since I know that I already have seen the spatial information a lot, and our image has been reduced to the very small representation. And if I just see the very small representation, there is no much local connectivity. So all the local connectivity has been distorted. Why? Because we already have applied a lot of convolution layer in the sequential order. So we left with only few pixels. So now I cannot connect these all the pixels. So spatial information has been distorted. So at the end, applying 3 by 3 filter or 5 by filter will not help you a lot because we do not have a lot of spatial information. Instead, we have a lot of channel information because by the layers you have increased the channel, increased the number of filters. And that's why your channel has been increased. So why not we should just aggregate the information in the channel? So at the end, we generally apply one by one filter. So this is the general practice, but it can be applied anywhere. But in general, we apply this one by one convolution when we feel that our image has been reduced a lot. Now a lot of spatial information is not there. So just apply one by one filter and just aggregate the channel information because now informations are there in the channel. So just consider it. And again, if you apply one by one filter, number of parameters you need to learn only few number of parameters because just applying one by one, so it's like only one by and 64 channel, then it's like only 64 values that you need to learn plus maybe 64 bias also, or not 64 bias, just one bias. And if you have like 32, then you have like 32. So in this case, if I find like if I ask you like how many parameters you have to learn, so you can easily say like for one filter I have to learn 64 into 1 into 1. So 1 into 1 is the filter size and 64 is the input channel, and I'm going to apply 32 such type of filter. So these number of parameters you have to learn. If I say like if I take 3 by 3, then it will be 32 64 into 3 by 3. So number of parameters are also lesser in this case compared to this case. Okay, so these are the advantages. One advantage is like number of parameters are less. Another is like it is just working on the channel. It is reducing the channel. And this is required when we have the global, or we can say the global representation of the image. It's like just at the end. So when we already have applied a lot of convolution layer, we already have seen a lot of spatial relationship. Now we left with just global information, or we can say like distorted information. So we do not have a lot of spatial connectivity. At that time, you just apply this and get the aggregate the channel information. This can be also work as a. This can be also replaced for the MLP layer. So sometimes we also use one by one convolution uh, instead of using fully connected. So we'll see this thing maybe when we'll go through the architecture part. Then at that time also I'll give you this all the idea. But one by one convolution is very cheaper compared to it's like very cheap compared to the this like your fully connected layer, because you know that if you are applying the fully connected, number of parameters that you need to learn is equal to the number of outputs into number of input, because you have to define the W matrix, and W matrix, the size of the W matrix will be the the size of the input into the size of the output. So that's why this is very, very costly. Suppose if I just see here, what is the size of the input? The size of the input is 56 into 56 into 64. So it's like these number of values that you are giving as input. And if you're trying to get these number of values as output, so it's like first you convert this thing into vector, this thing into vector, you're going from vector to vector. So it's like huge number of multiplication that you need to do. So what we generally do, instead of applying this fully connected, first we apply the convolution filter only. And what we do is generally apply one by one convolution. So one by one convolution is just like considering the value of the every pixel in the channel. And the very interesting part is that this one by one convolution is shared across all the pixels, which was not there in the case of fully connected. So in the fully connected, every row was giving one value. That means every row was responsible for getting only one value. So here the weights were not shared. So if you want to get one output, you need one set of weight values. But in the case of convolution layer, just one set of values can be applied at every location of the image. And that's the beauty of the convolution layer. So we generally apply this one by one filter instead of MLP, and just reduce the size of the image. So because if you just work on this and apply the fully connected, this will be very, very costly. So why not we reduce the size, reduce the channel, and finally once we reach to the very small size or very small number of channel, then you open it and then apply the fully connected. Because at the end you have to apply at least one fully connected, because you know that if you have to do the classification, then you have to apply one fully connected at the end. That will give you the class score. Okay, so let us see the summary. So we have seen that suppose we have given this image, C in into H into W, height into width, and this is the channel. And suppose you have kernel size KH into KW, the height of the kernel, height of the filter, and width of the filter. And suppose number of filters that you are applying is C out, padding is P, stride is S. Now if I say if I ask you like how many weight value that you have to learn, so number of weights will be what? The filter size, KH into KW, and channel will be also there. So C in into KH into KW, and you have, since you have C out such type of filter, so you will be having C out into C in into KH into KW. So these number of weight that you need to learn. You also have to learn the bias. So for every filter, you have one bias. So since you have C out filter, then you'll be having C out bias. Okay. Now, what will be the output size? So in the output size, channel can be decided very easily. So it depends on the number of filter. So what number of filter you are applying here, that will be your channel. So you are applying C out filter, so you'll be having C out channel. Now you'll be having new height, new width, and you know the formula of the height. So h new height is equal to the old height minus k, the size of the filter, kh plus 2p divided by stride plus 1. Similarly for the width, w dash equal to w minus k plus 2p divided by s plus 1. So these are all the formulas we already have seen before. Now, apart from this 2D convolution. So till now we have seen the 2D convolution. So whenever you have 2D convolution, Then we'll be having, suppose you have given the 2D image, and we'll be having 2D filter. Like, let us assume that we have a square filter, but you could be having a rectangle based filter also, like maybe height and width will be different. So this is the 2D filter, and the channel will come here automatically, and then you are applying C out such type of filters. This is the one scenario where we are applying 2D convolution. But suppose your input is not 2D. In this case, your input was image, and that's why you're applying the 2D filter. But suppose your input is 1D. Suppose you have 1D vector. Maybe you have some text, or maybe you have some like speech, or like this what we say this sound information. Okay, so in that case you do not have 2D information, you have just have 1D information. So if you have 1D input, okay, so in that case you cannot apply 2D filter. So for the 1D type of thing, again we have 1D filter, and that is called 1D convolution. So if I just see like what is the 1D, what should be the size of the 1D input. So in that case, you'll be having not these two things. Instead, you will be having only one thing. So suppose you have only W, and then for W you have channel. Okay. So you have width and channel. And now you have to apply the filter. So filter will be also having only one dimension. So we have only k dimension filter. But again, channel will come automatically. So channel, whatever channel we have in the input, that will come here. And you are applying C out such type of filters. Okay. So in that way, you can apply 1D convolution also. Now you can also apply 3D convolution. Sometimes you'll be having 3D image. So if you have 3D image, then applying 2D might not give you better result. Okay. So why not we should apply 3D convolution? Because you have to capture the 3D relationship. Because in the case of 2D filter, your 2D filter, 2D convolution is able to capture only 2D relationship. But since you have 3D image or 3D information, then just applying 2D filter will not help you. So why not we should apply 3D filter? So if you have 3D input like this, height, width, and depth. Okay. So these three information, and then we have channel also. Channel will be always there. So now we have to define the filter. So your filter will be of this dimension. Suppose you are taking the square filter. So Q filter, then we have K into K, the same size filter. And then channel C in will be match. And you are applying C out such type of filter. Okay. So you have like already these all the things already have been it's already there in the PyTorch. So whatever I have discussed here is just one line code in the PyTorch. So if you are going to apply 2D convolution 2D filter, you have just con 2D function. It's like already uh, this function is already there in the class is this con2d class is already there in the PyTorch. You just use it and define the layer. So you can define the layer, convolution 2D layer. You have also con 1D also there, con 3D also there. So just use it, and here you can provide all the information. So torch dot nn dot this is the we can say class. So inside the torch is the library, deep learning library, which you can use for building any type of neural network. And inside the torch we have neural network package, and then inside the neural network we have con2d class. Now this con2d class in the inside the in this con2d class you can define all the arguments. Like you can say like what would be the number of input channel, what would be the output channel, okay, what will be the kernel size, what will be the stride, what will be the padding, all those things you can put here. If you are not putting any information here, like some of the informations are must like this, some of the informations are like if you're not doing it, if you're not putting it, then it will take the by default value, like stride equal to 1, it's already there. So if you're not putting any stride, then it will take a stride equal to 1 by default. Padding is 0, so by default option is 0. Okay, so in this way like you can define the layer of the convolution. So either if you need 2D convolution, you just import 2D convolution. If you need 1D convolution, go for 1D convolution. If you need 3D convolution, go for 3D convolution. Okay, so I'll stop here. The next part is pooling, so that we'll cover in the next class. So now I'll be like you guys can ask question. Let me just yes, please go ahead. If anyone has any question, please ask.
One cross one, that one, you can you go to that?
Yeah, this one, na?
Yes, yes, sir, yes, sir. Actually, here, actually, I'm having some doubts. So,
Yeah, please, please.
where we should use? And the second point is how many layers we should have? Is there any calculation, or it is a hit and trial method?
No, how many layers? Again, this is heat and trial only. But when we will go to the CNN architecture, then you
Yes,
will
sir.
get to know like how many layers we should be having for solving particular type of problem. So actually, people already have done a lot of experiment in the past. So we'll be taking the advantage from them. So
Okay.
we'll walk through every standard architecture what have been proposed in the past.
Okay. And sir,
But here you just assume that it's just heat and trial. It's trial and error. It's just number of just take the layers and then see like whether you are getting good performance or not. If you're not getting, then you reduce the layers. Okay.
yeah.
Yeah.
So
So for
the
now, you
another.
just assume that this is yeah. Please go ahead.
Yes, sir. So then you told that multi-layer perception, right? MLP. And so we are just little bit confused. I means
Yeah.
MLP and conventional both are different, right?
Yeah, what I told you that MLP, this is like fully connected, na? MLP is your fully
Yes, sir.
connected.
Yes,
So
sir.
fully connect, your convolution can be also replaced uh, in the place of fully connected. So even because again we'll see this thing in the CNN architecture. So that time I'll like we'll show you like what is the advantage of doing it. So actually, since your convolution is like shared weight, so
Yes,
it's
sir.
just using one filter, you will be able to capture the information from every part of the image, and that's the beauty of the convolution. Okay, so like at the end, if you go with the MLP, because at the end, suppose you are doing the classification, you have to convert your image into vector, and then you have to apply the fully connected. Because for fully connected can only accept 1D vector, it cannot
Yes, sir.
accept 2D image. So if you are, even if you are getting 2D image, you have to convert it into 1D vector. Okay. So if I am converting this, suppose I got this image from the maybe from the last convolution layer, and if I am converting this into vector, the size of the vector would be huge.
Yes, sir.
Okay. And
Yes,
if
sir.
I'm going from this size vector to this size vector, number
Yes,
of
sir.
the size of the W will be also huge.
Mm-hmm. Yeah.
And that's the big problem in the case of fully connected, because your fully
Okay.
connected is the weight, the size of the weight matrix is dependent on the input size and the output size, multiplication of the input size and the output size. Okay,
Yes.
that's the problem in the case of fully connected. So why not we do some smart thing here to reduce this, the number of parameters. So what we do, we generally apply one by one filter first. So if I'm
Okay.
applying one by one filter here, so I'm
Yes, sir.
aggregating the channel information.
Yes, yes.
One by one filter is just I'm aggregating the channel information, because I'm
Mhm.
not looking the spatial information. And at the end, you just looking the spatial information is not informative, because at the end you will be having you'll be not having a lot of spatial information, because you already have reduced the image, and now
Yes,
you
sir.
just left with some pixels. But since you have channel, so you have a lot of information in the channel. Okay, so why
Yes,
not we should apply one by one filter and aggregate the channel, reduce the channels. So just reducing the channel will also reduce the size of the whole image.
yes, sir.
So maybe just reducing it, finally maybe we might be reaching to the one channel. So maybe
Okay.
56 by 56, 56 by 56, and 1.
One, correct.
Now your size is less. Now if you just open it and make the vector, that
Yes.
will be lesser compared to this size. And here also you have somehow aggregated the information using your filter. And the
Yes.
same thing we were doing in the case of fully connected also. We were aggregating the information every time. We
Uh-huh.
started with some number of values, then aggregated, and finally we'll be reaching to the 10 values because we had 10 classes. So here also we are doing the same, but we are
Yes, sir.
just playing smartly. Now, if you just see the parameter, number of parameter will be very less because every filter is having size one by one, and it will be also channel. So channel size will be something. So total parameter will be less only. And maybe
Yes, sir.
you'll be applying 32 such type of filter or 16 such type of filter. So again, in totality, number of parameter will be very less compared to the fully connected.
Yes, sir. Yes, sir. So, sir, on one last question from my side, that whenever we are putting a padding, right? So
Hmm.
padding, if you are putting zero, then how it will know that it is a padding bit or it is a actual data? You got
No,
my
actually,
question, right?
yeah, I got your question. So actually, what I said you that when we are applying this, your zero
Yes.
is padded in the outer area. Every
Yeah.
time you are adding the zero at the outer area only, na. So
Yes.
now suppose this is the image 7 by 7, and
Yes.
you want to apply 3 by 3 over this.
Yes.
Now your filter will be applied. You can only apply filter from here. You cannot start from here. You cannot start. These are
Yes.
like zero. Even you cannot put your filter at this point. So whenever I'm saying like I'm
But
going to put this filter at this point, that means I'm going to put the center value of the filter at this point. So what I told you, like I want to capture the information of every pixel of the image, which I was not able to do in the previous case because I was not able to consider the corner pixel as a center pixel.
no, sir.
That
So
was the
my,
issue.
my
Huh.
question is 3 into 3 means 9 pixel, right, sir? Out
Yeah,
of
yeah,
this
yeah.
out of this 9 pixel, if it is on the upper corner left, so
Hmm.
out of this 9 pixel, I'll have 3 plus 5. 5 pixels are zero.
Yeah.
So five
But at
pixels
least
are
it is
zero.
better than the previous. Na? Yeah, I understand your question. So you are
Yeah.
saying like five of are zero and remaining are like part of the image. So
Yes,
how
sir.
it will decide like which
Yes.
are from the image and which are from the
Yes.
outer
Yes.
area. So actually,
Exactly.
but at least this is better than the previous case. So at least you are getting some value for this center pixel. And how it will decide? It will learn that. So since we are going forward in a forward direction and finding the loss, and again we'll go back. So your filter will get to know like where I should give more focus, where I should give less focus when I am here at this point. So in that way, it will learn. It will try to learn. Again, there will be some noise. I like that since we have zero here, so that will give you
Mhm.
noise only. But at least you will be getting some value which we were not getting in the previous case. In the previous case, we were not able to capture the corner pixels. But in this case, at least you are capturing the corner pixel. I know that these pixels are like having zero value, but at least we have some pixels here which are having some non-zero value. And that will contribute. And if those values, because you are doing the dot product. So if
Yes.
suppose these pixels are contributing, at least you are getting some value for this center pixel as output. In the previous case,
Mm.
you are getting nothing for that. But now it's
Yes.
better than the previous case.
Okay. Okay. Because whenever
And
you
now,
you have your sliding window, sliding one
uh,
by one by one. So
mm,
for the uppermost, that means every time we are considering minimum three zeros. So you are saying as it is a dot product, then zero to any value that will be zero. So other
zero, zero
values will
only.
have the
They will not
significance.
contribute.
Yeah,
Mm,
that will have the. Okay, understood, sir. Okay, okay. Thank you, sir.
they will not contribute. But
Mhm.
again, since you are finding just multiplying and then a dot product and then summing it, yes, they will not contribute. But at least these pixels are contributing. So at
Yes.
least with the help of these pixels, you will be getting some value.
Mhm. Yeah, yeah. Okay, sir. Okay, understood. Thank you.
Hmm.
Hello,
Yeah.
sir.
Any other question?
Uh,
Please,
yeah, sir.
please.
Sir, have some confusions with the multiple approaches that we are taking. As an example, we're applying filter, right? And we're getting the spatial informations. At
Hmm.
the same time, when we're applying the padding, right? So
Hmm.
objective is to get the each and every like edges of the informations of the of the pixels, right? But
Hmm.
after applying the padding, we are not reducing the image size at all. So that means the
Hmm.
convolutions or operations we are not reducing, right? So
Hmm.
complexity is remaining the same, right? Time complexity.
Yes. Yes.
When we are applying style at the same time, we are not
Hmm.
taking the entire pixel information. We are just skipping
Yes.
some of the
Yes.
information, right?
Mm,
So
that's right.
how these are related? Like when while applying the style, we can say that somehow we are compromising on the output, or maybe it might not be actually correct predictions kind of thing.
Hmm.
At the same time, when applying the
Yeah.
padding, it will be like accurate, though it has the time complexity is much more.
Yes.
So
You're
if you
right.
can just
So,
highlight here.
yeah, you're right. So, when we are applying stride, you're losing a lot of information because you're not capturing every portion of the image. When you are doing zero padding and you're not your stride is one, then what is happening? Like you are getting same size output every time. So every time if you are getting same size output, your complexity will remain same because you have to do the same number of multiplication. Okay, but the important thing is when you are applying convolution, you are doing the zero padding, you are getting the same size output, but your representation is getting small. It is getting smaller. So suppose you had object this much object in this. Now applying the 3 by 3 filter will reduce the representation from this to this. The original, maybe I should add this. So your original size of the image will remain same. But in that image, only this much information is about object. Because like applying filter is reducing the size of the input now. It's happening. You are somehow you are managing to get the same size output. Why? How? Because you are adding the zero. But zero is not the part of the image. It's not part of the object. It's like noise that you are adding. So you will be having a lot of noises. Only this much representation you will be getting after applying few convolution. So by the layers, your representation is getting smaller. Your image size is same only, but in that image only this much part is useful. Other parts are like either zero or they are like just noise information. Okay, but I agree with your point that representation is if your size is remains same, then complexity will be uh, high. So for this again, we'll go for the pooling part. So I have not covered that max pooling part. So pooling will solve this problem. So we'll do the padding because we want to capture the corner information. But since we also know that if every time if you are doing the padding, your sizes remain same. So in that way, like your complexity is very large. So how to reduce the complexity? So that will come in the max pooling. So stride, I know that like stride again, you have to compromise with the you will be losing some information. So generally, in general we don't prefer uh, to take the stride more than two. Okay, so more than one. So we generally take a stride equal to one because we'll be losing information if you go with more than two, more than one. Okay, so that's why like in general what we do we take a stride equal to one only, but and we also do the padding. But we have some other thing which can also reduce the size. So one is like you can use the stride to reduce the size drastically. We have another hammer that can also reduce the size drastically. That hammer is your pooling. So that will come later.
Okay, sir. Got it. Got it.
Did you get your answer?
Yeah, yes, sir. Got it. Got it. Thank you.
Okay. Okay. Any other question? Okay, so I assume there is no question. So then I'll stop here.
Thank you, sir. Thank you.
Thank you. Thank you.
Thank you. Thank you.